Development of this tutorial was supported in part by NSF Grant 1432416. Any opinions expressed do not necessarily reflect the views of the National Science Foundation. Wireless communication systems require a high level of flexibility in order to meet the goals for current and future commercial, civil, and military markets. The number of wireless standards and protocols available calls for greater interoperability capabilities. These demands on existing wireless systems is driving the advancement of radios to be more flexible and incorporate more functionality. The software-defined radio provides a solution by offering greater functionality and flexibility than traditional radios. ITU defines an SDR as a radio that is configurable via software during operation of the radio. A radio that is able to change its operating parameters is flexible and can adapt to many situations. A block diagram representing the main components of an SDR receiver is shown. Although not always the case, to digitize the signal directly after the antenna input, down conversion to IF or baseband is usually performed before converting the signal from analog to digital. Directly digitizing the signal without down conversion can be achieved for low enough frequencies, up to a few gigahertz, but requires very expensive and complex hardware. The transmitter can be thought of a receiver in reverse. The transmitter can be implemented as in the block diagram shown, with the signal direction going from the DSP block towards the transmitter antenna. A comparison between conventional and software-defined radios is shown. The main difference is the greater flexibility of software-defined radios to adapt during runtime and be upgraded via software to meet the demand of a particular application. Quadrature amplitude modulation, or QAM, is a popular modulation scheme where the carrier is modulated in both amplitude and phase. QAM offers robustness compared to other modulation schemes that only rely on amplitude modulation. The higher the order of QAM, the higher the data rate. With higher order of QAM, a higher signal-to-noise ratio is required. In a scenario where the communication channel has high levels of noise, 64 QAM, for example, may not be possible. It would be advantageous for a radio to be able to sense the channel noise levels in order to adapt accordingly and choose an appropriate order of QAM. Spectral efficiency is the amount of data transmitted over a communication link per second per hertz. The amount of data transmitted refers only to the message sent or information delivered and does not include the bits used for error correction codes. Higher spectral efficiency can be achieved using higher order modulation schemes, but care needs to be taken since higher modulation schemes require, in general, greater SNR to avoid high bit error rates. Software-defined radios' flexibility help to increase the performance of radios and wireless communication systems by dynamically adapting to changing conditions of the channel. Also, SDRs provide the opportunity to upgrade its functionality via software upgrades, extending the useful life of the radios and adapting to new interfaces and diverse protocols. SDR's greatest potential is to manage and make more efficient use of the spectrum resources.